Hello and welcome to the continuing videos in the linear algebra series. So in this video, we'll talk about how to find the determinant in a slightly different way. The determinants by row reduction. So chances are, although I guess depending on the order in which you view these, it's technically possible you haven't. This is the first foray into determinants, but probably not. So the idea here is there are certain situations, especially when the size of the matrix gets big, where we might not want to be doing determinants just by the more direct method that you've already seen. Just because that turns into a bunch of little products that beyond 3 by 3s, for the most case, unless there's a lot of zeros that wipe out calculations, that the sheer number of calculations, once you get beyond a 3 by 3, makes it much more annoying to try and compute a determinant. So we want to see if we can come up with a way incorporating row reduction and a set of rules that if we use these elementary row operations, that we can compute the determinant either a little bit faster or change the matrix using row reduction to something that has a lot of zeros, where even if we use the methods we've seen before this, if there's a lot of zeros, then that means it's a lot easier because a lot of the computations gets wiped away. You don't have to find the cofactor if it's being multiplied by a zero, for example. So, and here we're going to talk about what the row operations we can do, and if we change the matrix with a row operation, what, if anything, does that do to the determinant? So the first thing to note is one interesting thing that works for determinants and determinants alone is that, so property 1, the determinant of A is equal to the determinant of A transpose. And if you remember, if we're using cofactors to compute a determinant, we can expand along any row or any column, which means it's not much of a surprise, or shouldn't be, that if you switch the rows and columns, it doesn't do anything to the determinant. So the nice consequence of this is while we tend to be very familiar with row operations, elementary row operations, anything we do a elementary row operation for can also be done using an elementary column operation. So if you decide you want to, instead of switching 2 rows, you think it might be advantageous to switch 2 columns. Well, that you can do in the same way you can do with row operations. Or if you want to add a multiply a row by something, and if you know what that does to the determinant, doing the same thing to a column would be the exact same thing. So this is the one and only situation. Can't do it for solving systems of equations, but you can actually use elementary column operations in the same way we use elementary row. That being said, most people by now tend to be very comfortable with row operations, less comfortable with columns. So there's no example that you solve that will require column operations, but there are some things that can be done more quickly if you did. All right. Second property that we have is if a row or column, so everything we're saying can be applied to rows or columns, of A is 0, then the determinant of A is equal to 0. And the idea behind this is row or column expansion. If you have a row of zeros, expand along that row. It is a bunch of zeros times cofactors. So 0 times C11 plus 0 times C12 plus 0, and so on, 0 times C1n. It's 0 times all the cofactors added together. It's just going to be nothing but zeros. So, in other words, the idea behind row is if we're going to row reduce, or column if you want, but we're going to row reduce, and then if at any point we get a row of zeros, the determinant is 0 and we're done. Otherwise, we can end up row reducing down to a special form, maybe the easiest form to work with, and then we can just, once we get to an easier form where we can read off the determinant immediately, then we can find the determinant that way. So these are the strategies we're going to apply. But there's a big question we need to answer in order to do any of this. So if A gets transformed to B, by a row operation, and again, replace row with column if you want a column operation. First of all, so two questions. One, does the determinant change? That's something we had to be concerned about with solving systems. If you perform a row operation, did the solutions change? We saw before the answer was no. So we need to know, does the determinant change? Ideally, the answer is no. But if it does, that's not a big deal as long as we know exactly how it changes. So if it does change, how does it change? And that's what we need to know. How does any row operation change to the determinant? If it stays the same, beautiful. If it doesn't change the same, as long as we know how it changes, then we know what the determinant of the original matrix would have to be. For example, if a row operation multiplied the determinant by 2, and then we figured out that the new matrix had a determinant of 10, then we knew the original matrix had to have a determinant of 5. So as long as we know exactly how the determinant changes, that's the next best thing to it just not changing at all. So there's 3 row operations we want to take advantage of, and that's what we're going to be looking at. So before we get to that, let's just make sure we know where we're going. So example, we'll call this property 3. The determinant of any triangular matrix is the product along the main diagonal. Notice how it doesn't have to be diagonal. Any triangular matrix. So if we think of that as to why that one might be true, if let's say we did 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, well, if we had this matrix, you could expand along the first column. That would equal to 1 times 5, 6, 7, 0, 8, 9, 0, 0, 10. And then the other entries, their cofactors don't matter because they're a bunch of zeros. And then you take the new matrix and expand along the first column again. 1 times 5, 8, 9, 0, 10, and so on. And so on. And we just get the product along the diagonal. So the point being is we're going to do row operations to try and turn our matrix either to a matrix that has a row of zeros or column, in which case we're done, or secondly, until it is triangular, in which case, just a quick multiplication along the diagonal will give us our answer. So that's what we're trying to use our row operations to do, is to get it into one of those forms where reading off the determinant is easy no matter what size of a square matrix we have. If it's a triangular matrix, it could be a 15 by 15 matrix. You just got to multiply along the diagonal. All right, so we're going to have 3 main rules in terms of what this is going to be. We'll call this a theorem. So our 3 main rules correspond to our 3 main row operations. Number 1, if B comes from A, by switching 2 rows or columns, then the determinant of B is equal to the determinant of A. And that's a gigantic lie because I forgot the negative. So if B comes from A by switching any 2 rows or columns, just switching them around, then the determinant flips sign. The determinant will change sign. So again, not ideal. Ideally, there would be no change. But the fact that it just changes to a negative, that's easy to work with. You just, if you do the determinant, you just have to keep track that the sign changed. Number 2, this one might make more sense. If B comes from A by row, J is K times row J. In other words, you're multiplying a row by K, then the determinant of B is equal to K times the determinant of A. The idea here is multiplying a row by K. If you expand it along that row, you're not changing the cofactors. The cofactors come from off the diagonal. What you're changing is the entry, so every A became K times A, but the cofactors didn't change. So in your determinant calculation, you just get this factor of K everywhere. And the last one is the weirdest. If B comes from A by adding a multiple of a row to another, then the determinant of B is equal to the determinant of A, and the determinant does not change. And so that one might be the weirdest one because, you're adding a multiple of one row to another. You might expect something to change, but the determinant doesn't actually change, which, it's kind of interesting, but certainly something that could be shown and, depending on whether or not I'm your teacher, something that we'll discuss more details about in class where, students can ask a few more questions. So what is this really saying? So this is saying that we can use these 3 rules, and we will use these 3 rules. And, all right, if we use the last rule, the determinant doesn't change. But if we use one of the first 2 rules, the determinant does change in a predictable way that we can use to say, all right, if we can find the determinant of B, if we know that we used this row operation with 3, and we know the determinant of B was 15, then we can get that the determinant of A was 5. And so we can always figure out what our new matrices, or determinant of the original matrix, is going to be. So that's what we're trying to accomplish here. So you start off with a matrix, use these row operations, keeping track of the changes, and then when you find that hopefully getting it down to triangular matrix, once you have the determinant of the triangular matrix, you can get the determinant of the original. And I'm sure there'll be plenty of examples in class. All right, that's it for this video. See you in the next one.